Hi, my name is Christoph Saulder and I'm currently a postdoc at the Max Planck Institute for Extraterrestrial Physics. I'm here today to represent the DESI collaboration and provide an overview of the DESI Year 1 results. In the process, I will explain to you the meaning of these contours. Naturally, I was just one of many people whose hard work and dedication made those results and the papers presenting them possible. You can see a list of people who substantially contributed to the DESI Year 1 analysis right next to me. Many of them are early career scientists who you might want to consider for future employment. In addition to the countless hours of work contributed by DESI members from all over the globe, we also need to thank our sponsors. Special thanks goes to the US Department of Energy, as well as our 72 participating institutions. Let's start with the basics. Most of you have seen a pie chart like this before. Thanks to cosmic microwave background observations by experiments like Planck and also other observations, we can constrain the present-day relative energy content of the universe. Only less than 5% of it is baryonic matter. Then we have about a bit over a quarter of dark matter, and the universe mostly consists of dark energy. The total amount of energy and the amount of dark energy define the expansion history of the universe. It is a little bit embarrassing to admit that we know little about the nature of dark matter and even less about dark energy. However, by the end of these talks, we will know a little bit more about the nature of dark energy thanks to DESI. The Dark Energy Spectroscopic Instrument is installed on the Mail telescope on Kitt Peak in Arizona, within the lands of the Tohono-O'odham Nation. In May 2021, DESI embarked on its 5-year mission to survey over 14,000 square degrees of the sky, to seek new galaxies and to boldly take spectra no one has taken before. DESI is a multi-object fiber spectrograph with 5,000 robotic fibers that can be arranged over an 8 square degree field of view. The unique design of the DESI focal plane allows it to gather redshifts at an unprecedented rate. Behind me you see part of this focal plane that is home to 5,000 robotic fiber positioners. The fibers are fed into a spectrograph which allows us to measure up to 5,000 spectra in a single exposure. Then the focal plane can automatically reconfigure the positions of the fibers for targets for the next exposure. On a night with perfect observing conditions, we are able to obtain up to 200,000 extragalactic redshifts, which corresponds to more than one 6-degree field galaxy survey in a single night. In this movie, you can see the operations of DESI over the course of a more typical night. Near sunset, while the moon is up, it carries out bright time observations. Once the night has become sufficiently dark, DESI switches to dark time observations to measure spectra of faraway galaxy. This way it builds up its 14,000 square degree footprint over the course of many nights. Around sunrise, a few more bright tiles finish out the nightly observation run. The primary science goal of DESI is to measure redshifts of about 35 million galaxies and quasars over a large redshift range. and thereby constrain the expansion history of the universe using baryon acoustic oscillations, short BAO. The main tracers are the bright galaxy survey, the luminous red galaxies, the emission line galaxies, and quasi-stellar objects, each with their own characteristic redshift range. Within its first year, DESI has already measured 5.7 million unique extragalactic redshifts below 2.1. They consist of the previously mentioned 4 tracers, BGS, LRGs, ELGs and QSOs. They cover an effective volume of 18 cubic gigaparsecs, which is already a factor of 3 larger than SDSS. The data is split into 6 redshift bins to probe the expansion history of the universe. Additionally, to probe the regime above a redshift of 2.1, we use 420,000 Lyman-alpha quasars. Within just 1 year of DESI observations, we obtained already twice as many as in 20 years of SDSS. With all that amazing data at hand, it is time to explain how we are going to use it to measure the expansion rate of the universe as a function of lookback time. In order to bring everyone to a more or less equal footing, I will start by explaining the main science driver of DESI, the baryon acoustic oscillations, short BAO. They are the imprint of the maximum distance that the acoustic waves could travel before recombination. As you can see in this animation, we start with some primordial overdensity in which the photon baryon plasma is forced into. However, the photon pressure will cause fast acoustic waves to propagate outwards. This, of course, is not only happening in one overdensity, but all of them. At recombination, the pressure drops and essentially freezes the pattern of the density distribution of baryons. This will impact where galaxies will form, and we can detect this feature as an increase in number density at a certain distance. The distance scale imprinted in the BO is the maximum distance acoustic waves could travel before recombination. Afterwards, it only scales with the expansion of the universe. This allows us to measure the expansion history of the universe by measuring the BO in different redshift slices and thereby constraining cosmological parameters. We do not only measure the isotropic BO scale, but also the anisotropic one. If the shell of the BO scales differently orthogonal to the line of sight when compared to a fiducial cosmology, we obtain alpha perpendicular. It constrains the co-moving angular distance. On the other hand, we can also consider if the BO scales differently along the line of sight when compared to a fiducial cosmology. This yields alpha parallel, which informs us about the Hubble parameter distance. Of course, by switching bases, we can decompose this into the isotropic BO, which gives the overall change in size compared to the fiducial cosmology, and the anisotropic or quadrupole of the BAO according to the Alcock-Baczynski effect. The universe doesn't consist of the BO alone in isolation. The BO signal gets blurred and washed out during the growth of structure and also due to the distortions by peculiar velocities. However, since we also observe the matter distribution of the universe, we can model a displacement field. We can further use this information to move the galaxies into the opposite direction of the gravitational pull and thereby approximately recover their original positions. This allows us to get a much clearer BO signal. This method is called reconstruction. In order to obtain the scale of the BO, we use the two-point correlation function. Therefore, we measure the distance between all possible pairs of galaxies and adding them up in a histogram. This animation here is cheating a little bit, because in order to obtain the shape shown in the plot, we need to normalize this distribution by using a random catalog covering the same volume. The most common way to do this, which we also use, is by taking the Landis-Delay estimator. It takes advantage of the cross-correlation between the data catalog and the random catalog, in addition to the autocorrelations of the data and random catalogs respectively. Alternatively, one can also do the Fourier transform of it and measure the power spectrum. As explained before, the relative difference in the BO scale between a template based on fiducial cosmology and the observations is called the alpha parameter. We can do this perpendicular to the line of sight, along the line of sight, or take the isotropic average by combining both. Therefore, we can obtain the co-moving angular distance, the Hubble parameter distance, and the co-moving volume distance respectively. These parameters directly relate to the base cosmology, and with a little bit of math allows us to constrain the dark energy content and curvature at different redshifts. Different dark energy equations of state will result in a different expansion history of the universe, which we can probe with our BO measurements. Using the CPL parameterization, we can even predict what we would expect for a large range of models with time-varying dark energy. In addition to the usual discrete tracers, such as various types of galaxies and quasars, there is an additional way to measure the BO at very high redshifts by using the Lyman-alpha forest. As we see the light of a high redshift QSO traveling towards us, it passes gas clouds of the cosmic web. Their light at the local rest frame wavelengths corresponding to the Lyman-alpha transition of atomic hydrogen is absorbed, and thereby creating a line for each gas cloud it passes on its way. This builds up a forest of absorption lines in the spectrum. If you pay close attention to this animation, you will notice a second line for which this happens, Lyman beta, albeit at a smaller magnitude for this weaker line. The redshifts of the various lines indicate the positions of gas clouds along the line of sight between us and the quasar. This allows us to calculate the autocorrelation function between these clouds, as well as the cross-correlation function between the clouds and the quasars. Given the size and quality of the DESI Year 1 dataset, we are able to obtain the correlation function between Lyman-alpha absorbers and Lyman-alpha absorbers, but also between Lyman-alpha absorbers and Lyman-beta absorbers. We can also get the correlation functions between Lyman-alpha absorbers and quasars, as well as Lyman-beta absorbers and quasars. However, at this high redshift range, the signal noise limitations prevent us from using the autocorrelation functions of quasars and the autocorrelation functions of Lyman-beta absorbers. With our methods in mind, it is time to shift gear and discuss how the DESI analysis is different from other surveys before. Aside from the amazing achievement of it being the biggest dataset so far, we also have conducted a blind analysis on catalog level for the first time. This should help us mitigate confirmation bias. We have already determined the baseline methods and systematics before unblinding. We also had to determine which tests and changes were allowed after unblinding, such as choices of the covariance, bug corrections on the catalogs, and some final mock tests for systematics if the central values were offset. Furthermore, we used a unified BO analysis pipeline for all tracers over a large redshift range. We also implemented physically motivated improvements to a BO fitting method and developed a new reconstruction method. Additionally, we use a combined tracer to deal with the overlapping redshift range between LRGs and ELGs. When testing for systematics, we didn't find any for observation effects, the reconstruction choice, or the choice of analytic covariances. Overall, all systematics are well under control and significantly below the statistical error. So, now, the most interesting part of the talk begins. We have the data, we know the theory, we have discussed our methods. So, let's get started with some DESI Year 1 results. First, we look at bright galaxies between a redshift of 0.1 and 0.4. Then we add two samples of luminous red galaxies at redshift ranges 0.4 to 0.6 and 0.6 to 0.8. For the redshift range between 0.8 and 1 we consider a combined tracer of both luminous red galaxies and emission line galaxies. Then we solely look at emission line galaxies at a redshift between 1.1 and 1.6. For redshifts between 0.8 and 2.1 we also consider our quasar sample. For the highest redshift bin between 2.1 and 3.5 we use our Lyman-alpha samples. This dataset is unique in more ways than one. For example, we have a strong BO detection of 0.8% thanks to our combined tracer at an effective redshift of 0.93. Additionally, we managed to get a solid BO detection for ELGs for the first time at an effective redshift of 1.32. Overall, our aggregated BO distance precision of 0.52% is already exceeding the quality of all SDSS BO measurements of the past 20 years. And keep in mind, this is only with the first of at least 5 years of DESI data. We also compared the unblinded data to the detailed tests carried out on mock catalogs. Everything is consistent. This is the Hubble diagram derived from DESI Year 1 data alone. We were only able to do a reliable full 2D analysis of the BO for some of our redshift spins with the best data. When comparing to previous datasets, one can clearly see the overall improvement in quality and quantity of data thanks to DESI. These figures show the isotropic BO and quadrupole, while here we show the same data expressed in transverse and line of sight. The keen observer will have already spotted tensions between the SDSS-based eBOS and BOS data and the DESI Year 1 data. This is especially strong in the 0.6 to 0.8 redshift bin. Despite an almost 3 sigma tension, the data there is only weakly correlated. We conclude that the difference is consistent with statistical fluctuations. something supported by an upcoming paper of yours truly, we also want to stress that DESI did do a blinded analysis. Naturally, we also did a reanalysis of the SDSS, in particular BOS and eBOS LRG data, using the DESI pipeline. We found that the results based on the SDSS data stay pretty much the same even with the DESI pipeline, and the tension only gets minimally lowered. These tests were done extensively and carried out for various different reconstruction schemes, 1D, 2D, BO measurements, different fiducial cosmologies and more. However, the tension is not caused by our pipeline, but the different datasets themselves. In addition to all the careful tests of galaxy and QSO data, we carried out a comprehensive series of tests for the Lyman-alpha data as well. In addition to mock tests, we also split the data into various samples to test consistency and variations for the blinded analysis. Here we just show a glimpse of all the tests. Just to illustrate the strengths of our blinding strategy, in the case of the Lyman-alpha data, we show the SDSS DR16 alpha values compared to results obtained from the DESI year 1 data before unblinding. Now we add the results after unblinding. One can clearly see how much of a difference the blinding made. It also shows that we were not subconsciously drawn towards the SDSS DR16 value, despite the extreme blinding. Also, for the Lyman-alpha data, both autocorrelation and cross-correlation yield consistent results. After illustrating the quality of the unblinded DESI year 1 data in great detail, it's time to move on to the cosmological constraints that we can derive from it. So let's play the game again. First we add the BGS, then LRGs, then LRG cross ELG, then ELGs, followed by QSO, and finally the Lyman-alpha data. One can clearly see that they are consistent with each other and complementary, as the bananas overlap at different angles. Thereby we obtain a matter density of about 0.295 and a Hubble constant times the drag radius of 101.8 kilometers per second. Next, we want to compare DESI to other cosmological probes. First, we add the SDSS BO measurements to our plot. Despite some offset of the central values, there is considerable overlap. When adding the CMB, we can see that there will be additional constraining power. By combining the CMB and DESI BO, we are able to get an omega meta measurement at 1.6% accuracy. In addition to measuring omega meta, we can also constrain the present-day Hubble parameter when taking into account Big Bang nucleosynthesis. Thereby we find an H0 of 68.52 plus minus 0.62 kilometers per second per megaparsec when taking into account DESI BO, Big Bang nucleosynthesis, and the angular size of the BO at recombination. Also, this value is marginally higher than other early probes. It is still in agreement with the CMB and consistent with SDSS. However, the Hubble tension to late probes from SHOES remains at 3.7 sigma. As the neutrino mass estimate from the CMB are limited by internal degeneracies, DESI BO can break them due to their constraining power on H0. Assuming a lambda CDM cosmology, we get an upper limit on the sum of the neutrino masses of 0.072 electron volt, which is already very close to the lower limit of 0.059 electron volts coming from neutrino oscillation experiments. However, if we allow for a time-varying equation of state for dark energy, the upper limit coming from the CMB in combination with DESI BO relax to 0.195 electron volt. One of the main goals of DESI is to better understand the nature of dark energy. There is a good reason why this makes up half of the name of the experiment. Hence, we want to see how well DESI year 1 data can constrain the dark energy equation of state. Assuming a constant equation of state parameter W, we are very consistent with the cosmological constant. For comparison, we can add the CMB constraints to this plot, as well as various supernova samples such as the Pantheon's plus sample, Union 3 sample, and the DES sample. Combining all these probes allows us to provide an even tighter constraint. The results are still in agreement with the cosmological constant as long as we assume a constant equation of state for dark energy. With that said, let's see what the DESI year 1 data says if we relax that assumption and allow for a time-varying equation of state. We use the Chevalley-Polar-Cylinder parameterization with the two constants W0 and WA that allow for the dark energy equation of state to change with the relative scale of the universe A. A cosmological constant would correspond to a W0 of -1 and a WA of 0, which is still compatible with the DESI BO data alone, although it already favors a time-varying dark energy. Merely adding the CMB data to the set, we get a 2.6 sigma preference for a time-varying dark energy. DESI plus various supernova samples, such as Pantheon plus, Union 3, DES year 5 supernova also favor time-varying dark energy at different levels of significance. Hence, combining all three probes, DESI BO, the CMB, and a supernova sample will yield the strongest constraints on the dark energy equation of state. When combining DESI BO, the CMB, with the Pantheon plus supernova sample, we find a preference for time-varying dark energy at 2.5 sigma. In case of combining them with Union 3, we get 3.5 sigma, and for the combination with the DES supernovas, we find a 3.9 sigma preference for a time-varying dark energy equation of state. For any supernova sample, the three probes combined show a clear preference for a W0 greater than -1 and WA less than 0. This figure here shows how the equation of state of dark energy evolves over time, based on the best fits to results of DESI year 1 plus other probes. DESI year 1 has already provided the most precise galaxy BO measurements with an aggregated precision of 0.52%. We also provide the first BO analysis with catalog level blinding and a unified analysis for all tracers over a wide redshift range. We have the highest precision for galaxy BO above a redshift of 0.8 so far, and the first significant BO detection for emission line galaxies. Already with the first year of DESI data, we have observed 420,000 QSOs above a redshift of 2.1, which is twice as many as all of SDSS. We have the most precise BO measurements to date between a redshift of 2 and 4 thanks to the Lyman-alpha autocorrelations and the Lyman-alpha quasar cross-correlations, thereby obtaining Lyman-alpha BO scale at a precision of 1.1%. On the cosmological side, we can constrain H0 to 1% by combining DESI, Big Bang nucleosynthesis, and the angular size of the sound horizon at recombination. The tension we choose remains. We have improved the constraints on the sum of the neutrino masses. The DESI data is consistent with a W equal -1 if the equation of state of dark energy is assumed to be constant. However, when we allow for time-varying equation of state, DESI and the CMB yield a 2.6 sigma preference for a W0 WA cold dark matter cosmology with W0 greater than -1 and a negative WA. Adding supernova samples, we can get even up to 3.9 sigma. Not all DESI 2024, or as I call them DESI Year 1, key papers have been released yet. The results presented here are based on the 3 key papers published this April. The remaining papers will be released later this year. In addition to the key papers, there are about a dozen support papers for each key paper, many of them already published. These papers explain scientific methods and tools used for key papers in much greater detail and provide supplementary tests and results. You can find an up-to-date list of all DESI papers using this link. Again, I want to stress that all these amazing results are just from 1 year of DESI observations. In April this year, we have completed the data collection for year 3 that covers a much larger area on the sky. For bright time, we have already started an additional pass. And dark time observations are over 2/3 complete. For the year 3 analysis, we will focus on slightly different key projects as we did for year 1, before bringing everything together for year 5. Currently, DESI is a couple of months ahead of schedule, despite forest fires and slipping E-chains. The DESI Year 5 dataset will be 3 times larger than the DESI Year 1 dataset. Assuming the central value stays more or less the same, DESI Year 5 will be able to provide even stronger evidence for a time-varying dark energy equation of state. DESI Year 5 might not even be the end of DESI, as plans for extensions and even DESI 2 are in preparation. Thank you, and I'm looking forward to answer all your questions, either during the live discussions or any time on the dedicated Mattermost channel.